Let's discuss some basics of how inverters are architected before we get into discussions of transformer, transformerless, low frequency, high frequency, and whatever. Low frequency inverters were the first technology for inverters that was ever out there, and it was your basic transformer output technology with a couple of power devices. And when I talk about power devices, they might be MOSFETs, IGBTs, a whole host of different technologies, which is totally irrelevant, actually. So there's always a couple of power switches in the circuit. It accepts your DC input. The transistors switch alternately on each half into a transformer that then steps up the AC output. And the very earliest inverters might have had what is called a square wave output, which simply went up and down and generated the AC output. As the world evolved, there ultimately was another topology, which is called a full bridge, which accepted the DC input. And during one phase, this transistor and this transistor were turned on, and that developed a positive on the upper half. And in the alternate phase, the opposite two transistors came on, which put the upper lead more negative. And then coupled into a transformer, and this actually simplified the transformer a little bit because it didn't need a center tap. But one of the developments in the world of the low frequency square wave type inverters was the concept of the modified sine wave, as shown by the dotted lines. And the idea of the modified sine wave was to represent as accurately as possible the energy content of an equivalent sine wave during that interval, so that the power became a little bit friendlier to the loads that you had. So the high frequency inverter uses multiple high frequency DC to DC converters inside of it. Here's what's inside a typical DC to DC converter, and I've shown 4 of them here. They accept the DC input, and those converters then step that DC input up to a higher voltage, which goes to an output switching circuit that operates at that higher voltage. And in this example, we've shown the input voltage converted to a plus 85 and minus 85 volt rail. And why plus and minus 85? Well, the reason for that is because the peak value of a 120 volt sine wave is 168 volts. And so this gives us a total of 170 volt capability on our output stage. And again, this full bridge controller, when these two transistors are on, you've got plus up to 170 volts. When these two transistors are on, you've got minus 170 volts. And so the actual switching in the output stage are still technically low frequency, but it's called high frequency anytime you use the DC to DC converters internally to step up to a high voltage output stage. And again, the particular circuit we're showing here is targeted at generating a modified sine wave. Now in our next segment, we'll start to talk about sine wave inverters and how we get there. You may or may not have noted that since we've been talking about the high frequency inverter, that the output is transformerless, which is another secret to the transformerless inverter technology. Now, the next thing to talk about here will be sine wave outputs and how we get there. So taking that high frequency transformerless inverter, how do we get there? Well, with the modified sine wave output, this part of the circuit switched at 50 or 60 hertz. Of course, these DC to DCs, they're the high frequency components. They could be switching in terms of hundreds of kilohertz. And again, for a modified sine wave, this switches at 50 to 60 hertz. But we want to get a real sine wave out of our inverter. So what we do to accomplish that is we're going to have to switch the main output switches much faster and then turn that back into a sine wave. And by much faster, it needs to be at least 10 times the fundamental frequency. Like for 60 hertz, you need to be at least 6 kilohertz. And generally these stages switch somewhere around maybe like 40 kilohertz to accomplish their function. And what they use is a thing called pulse width modulation. And their output is either high or is either positive or negative. And the way that they create the sine wave is that during the positive intervals, you'll see that the switching spends a lot of time on the positive half. And as we swing more and more negative, you can see it's spending less time in the positive. And right around zero, it's about 50-50. You spend equal time high and equal time low. And when you go negative, you see that you're spending a lot of time in the negative region. So when you filter and take the average of these pulses over time, they can be shaped back into a sine wave. So the only other addition needed to accomplish this would be an output filter network, which filters out the very, and this graph is not to scale. The actual switching frequency would be much, much faster than shown here. And this is just for illustrative purposes. And this output network will be necessary to be able to filter that and to return a sine wave output. Now again, we're talking high frequency transformerless inverters here. And in our next segment, we're going to discuss transformer versus transformerless. Now we'll talk about the subject of transformers in inverters, because aside from high frequency, low frequency, we also have transformer versus transformerless. And transformerless inverters at first glance have advantages in terms of weight. Transformers are big, heavy things, and transformers are not exactly cheap. And you get somewhat of a incremental increase in efficiency in the transformerless inverters. I'm a little bit confused with people that particularly go with off-grid solar and they're concerned for efficiency, because if your power's free, how come you don't just buy more panels and make up however much power you need regardless of the efficiency of the equipment you've got hooked to it? To go off-grid solar and, you know, scrimping and saving for power just seems contradictory to me. Now, transformer inverters have their set of advantages too. First and foremost is safety. Because if anything goes wrong in the semiconductor portion of the circuit that causes something like a large DC output, or one of these transistors is shorted, it cannot ripple through to the output. The only thing that can get to the output is true AC. The other thing is ruggedness. The transformer makes it possible for the circuit designers to more effectively design protective circuits such that they can better protect their output devices against overloads and short circuits and all manner of things much more reliably than you can when your transistors are connected directly to the outside world. Lastly, that provides full isolation from the input side of the inverter, which gives you a lot of freedom in what you do with that AC output. So the transformer has a lot of efficiencies, or I mean a lot of advantages also. And you can also put a transformer on the output of a transformerless type circuit. So whether or not it's transformer or transformerless doesn't have anything to do with necessarily with the high frequency, low frequency term. So now that describes the basics as to the advantages and disadvantages of transformer versus transformerless. And next we're going to go into a discussion on the transformerless inverter and the ramifications of a failure in one of those output devices. So here's the issue with your transformerless output that's the most concerning. Let's say that one of the output transistors in your bridge circuit fails, and fails shorted, as can occur. It directly connects that plus 85 line to the output line that it's connected to. The remaining line may still be capable of switching, it may not. You can even have problems, not just a shorted device, but the control circuitry could have failures in such a way as to keep just one of these devices on constantly and giving an equivalent failure mode. And the danger here is that you're now putting DC, high voltage, high current DC, out onto the power line that goes into the house. I can hear it already, but that should trip a breaker. Well, you know what? If you're really lucky, in a lot of cases, that's exactly what's going to happen. Because there's some loads out there, things like motors and any type of electronics that have transformers in them, which are still manufactured, that are going to consume high currents at DC. But sometimes you may not have that much current flowing to trip a breaker. And so there's nothing left in this circuit to stop the current flowing under this fault condition. I personally have had this happen. I'm inside the house, I got a short on an AC outlet, it failed the inverter, and I didn't even realize that it had failed it and was outputting DC until I smelled some nearby electronics getting hot, and luckily I went out and disconnected the inverter before it led to any damage. And the problem is the current just isn't high enough to trip a circuit breaker. And of course, the inverters are not built with circuitry to specifically detect this type of failure. And if it detects the failure, there's only one viable solution, and that's to incorporate a mechanical type of a relay to open that circuit. You can't save a semiconductor device with a semiconductor device. So we're going to explore this problem a little bit more as we progress here. But wait, silly me. Everybody knows that semiconductors don't fail. Output switches don't fail, especially shorted. If I was an inverter manufacturer, I'd give a lot of thought to the consequences that may occur due to the failure of just a single transistor in somebody's solar power system. As pointed out, you don't even have to have a high current failure to potentially bring about a problem that you never thought could occur in your system, but it appears that it did occur anyway. So good designs that are intrinsically safe in the event that they fail will definitely give you a cutting-edge product that a lot of people don't seem to be interested in doing. To illustrate the failure mode that I'm going to discuss on the Sine output transformerless inverter, which is a failure of an output transistor and its effect on the output signal and the dangers to the outside world, I've built a SPICE simulation of a Sine output transformerless inverter, and the left side starts with a pulse width modulation circuit which generates the pulses to drive the MOSFET gates, and I had to make some models of MOSFET gate driver circuits, but the core of it is I've got 4 MOSFETs and properly driven in such a way to give a 25 kilohertz PWM square wave frequency, and then I go to an output filter to recover the sine wave, which I've set it up to produce a 50 hertz sine wave so that 50 hertz is synchronous with the 25 kilohertz switching frequency that I've got to illustrate this. Now, to make this simulation operate, normally what I would do here is I would start a transient analysis, and I would end the transient analysis after 500 milliseconds, but I would actually start the display of the result at 450 milliseconds, because that 0 to 450 allows some settling time, because when it's like any other circuit, you turn it on raw, it has to go through some settling till it gets to correct output, and then that final 50 milliseconds shows those actual outputs. But that simulation will require 10 minutes. So what I have done is I have conveniently stored the simulation result that was done previously. And what you can see in this waveform display is, first of all, let's look at the voltage output, which, as advertised, is a clean sine wave output, and it's going from about minus 200 to plus 200, which is a little bit high, and the current is going from plus 30 amps to minus 30 amps, and there's a little bit of phase shift in there. I used the 29 millihenry inductor with 1 ohm in series to try and emulate a load like a motor that's got some significant inductance in it and very low resistance in it. And so again, that's what the sine waves look like. Now, to see how those sine waves come about, what we can do is zoom in on the pulse width modulation. And you'll note that when the sine wave is close to the negative limit, that the pulse width modulation pulses are also spending most of their time negative. And when we look at the corresponding positive interval, of course, we're going to see exactly the opposite thing. We go in a little bit closer here. When it's up positive, you can see that the pulse width modulation is mostly positive. And of course, if we focus on a zero crossing, you can see that the pulse width modulation is very close to equal duty cycles on either side to create zero. So that's our basic pulse width modulator operating properly into a 29 millihenry 1 ohm load. Now the next thing that I did was I took the same circuit and I emulated a blown shorted transistor by putting a short directly across one of the transistors. That's the only thing that's been done in this circuit. So we could look at the results and why that's significant. So we go to the results for the broken inverter. Oh, well, look, those sine waves look just fine, don't they? I guess we're done. Wait a minute. Let's look a little closer here. Look at the voltage output. Look at the negative level is 0. And it goes up to a positive level. Actually, probably about 150 volts or so. It doesn't go through 0 like a normal sine wave. That's what I talk about when I talk about that failed transistor puts a definite DC component into your AC output. And while this looks like a sine wave, if you integrate all that, it really looks like DC. It's got a DC component at about half that peak value. In fact, we'll just measure it here. It looks like that DC component sits about around 102 volts or so. So it's got a significant DC component. But what's even more interesting, even when the AC voltage is at 0, we have almost, and where did my little results go? They went here. We have almost 93 amps of current flowing at the negative excursion of the sine wave current, and at the positive excursion of current, 115 amps in a load that normally pulled plus or minus 30 amps. That's exactly the danger. These inductive loads or transformers or any similar type device in your home or your loads are very, very much at risk. And those kind of shorts, if allowed to sit around and without anybody turning something off or fuse blowing or something, you got the potential for a fire. And these shorts or these currents, due to the blown transistor, don't always get real high. they can be low. They can be lower than your circuit breakers. But the fact that they're flowing and flowing continuously into possibly a small little wall wart or something can spell disaster in terms of fire danger. So that's basically what the shorted transistor does to the transformerless inverter output. And again, a manufacturer who wants to make a top-tier transformerless inverter is also going to include a relay in this output circuit. And that relay will only be turned on when the inverter is delivering a correct output. If the circuit detects that it's deviating anyway from the correct sine wave, or that there's a DC component, it will shut the relay off. Now there's other things besides shorted MOSFETs that can cause this condition. A controller or the controlling circuitry can develop faults that can look exactly the same way, that somehow they're providing a turned on gate drive at all times. So the cause of this particular defect can occur in several points within the transformerless inverter circuit.